Now, the very last functions we're going to learn differentiation rules for in this section are the sine and cosine functions. So let's start off with f of x equals the sine of x. And just as a note here, from this point forward, I really do need my sine and cosine functions always to be in radian measure, even if I'm using a different letter for my variable. The reason for that is that when we calculate the derivative really does expect this to be in radian measure. When we convert to angle measure, or goodness, even grads, any French scientists in here? Grad measure for angles? No? Okay. Then that conversion will actually affect the derivative. So we are going to be using radians for all of these derivative calculations. Let's look at the graph of my sine function. Here on top, graphed in blue with some pink tangent lines to boot, is the function y equals sine of x. In pink below it is its derivative. So at every x coordinate, we have figured out the slope of this tangent line, just geometrically here, and we've plotted it out. So I see all the places where the sine function has a horizontal, all the places where my sine function has the horizontal tangent, my derivative is going to be 0. All the places where the sine function is decreasing, my derivative is negative. All the places where my sine function is increasing, my derivative is positive. Sounds like a derivative so far. But what shape is that? Ooh, this is a periodic function. At 0, my periodic function is equal to 1. After 2 pi units, my function repeats itself. It's equal to 0 at pi over 2. It's equal to -1 at pi. My gosh, could this be the cosine? Well, yes, it is. But why? Why is this the cosine function? Let's actually build up the derivative for the sine of x function. And I do have to use my limit idea again. So limits are still important. We will be taking the limit as h goes to 0 of the function, sine of x plus h, all minus sine of x, and that whole mess divided by h. Well, okay, I can use my angle addition formula on it. Now, so far in this class, we've only been using angle doubling formulas, but this is the angle addition formula for 2 different angles of different measures. So my sine of x plus h will be equal to sine of x times cosine of h plus cosine of x times sine of h. And if that seems a bit unfamiliar, then perhaps go back and look at some trigonometry or send me an email. I'll be happy to talk about it. Now we've broken up this fraction like so. Inside the limit, I have the quantity sine of x times cosine of h minus sine of x all on h. And then I have to add to this cosine of x times sine of h all on h. Well, hey, over here's my cosine function, not quite all by itself. And over here, I have some other stuff. So let's simplify again, get all those h's together in one spot. I have the limit as h goes to 0 of sine of x times cosine of h minus 1 all on h. And then that is added to cosine of x times sine of h on h. Well, hey, sine of h on h, as h goes to 0, the variable is different, but that was one of the first limits that I taught. This limit is equal to 1. Now, your book goes into a lengthy trigonometric argument, building up a right triangle and following angle measures in here to show why this idea works, to say that sine of theta on theta must always be greater than cosine of theta and less than 1. I find the pictorial argument much more convincing. So here in red, I have my sine of h on h function, h going to 0. I know it's always less than 1, which I've graphed here in green. I know it's always greater than cosine, which I've graphed here in blue. So by the squeeze theorem, what can this limit be besides 1? Let's go back to those slides. So this limit is going to be equal to 1. What about my cosine function? The cosine function is looking a little bit more complicated. So with some tricky algebra, we're going to multiply by the conjugate. Oh, it's not just for square roots anymore. So what do I get on my numerator? I have cosine squared of theta minus 1. I have denominator theta times quantity cosine of theta plus 1. Well, hey, that numerator is just a sine squared. I like sine squared in this limit because this is the limit of sine of theta on theta times the limit over here. So I get negative 1 times, well, sine of 0 is 0, cosine of 0 is 1. This fraction must be equal to 0. So my other limit here is equal to 0. Altogether, f prime of x has to be the cosine. I'm a little bit over time for this video, so you might want to rewind and see where these limits fit back into this formula here. Limit is equal, we're taking the limit of sine of x times a thing that's going to 0, plus the limit of cosine of x times a thing that's going to 1.